Thank you. Thank you for coming back to the second part of this lecture. In principle, the three parts are not necessarily connected. They are around the same topics, so you don't need to have been here in the first part. But I left out a few things on my first lecture, which was mainly based on computational complexity and the use of effective dimension for computational complexity, and I like to point out to them. So you may have a look at my slides that are, I think, online. I didn't have time or didn't manage my time properly to talk about open problems. So you may want to think about which is the polynomial time dimension of MP, which even if we assume a strong hypothesis of MP being different from P, still it's got a lot of possible answers. Since remember I told you every class has a dimension, or polynomial time dimension. There are many possible answers. The second one is on what we call partially complete problems. That is, for instance, partially complete problems for exponential time, meaning that there is a non-zero subclass of exponential time that reduces to them. So do they exist? Are there interesting cases? And also, the third one, or the third sort of class of open problems, is BPP sources. We know that Martin law of randomness is enough to have to be a good BPP source. We know that we can put resource bounds on that and get polynomial time randomness, etc. That is enough to have a BPP source. What happens with dimension? It's not so clear there. There are certain problems both to look at yes, effective dimension and resource-bounded cases as BPP sources. And also, I left out references because I didn't put them very much on the slides. I left them to the end, and then I never got there. So please have a look at the references, especially if you're interested in learning more. Yes?
So can you use a sequence of with dimension less than 1?
Yeah. So for which kind of oracles can you have this? Sorry. Okay. This kind of thing. I prefer not to talk about this too much. I already talked about a little bit about computational complexity, but since I don't seem to, time seems to go fast, at least from the experience of the first day. Let me move to what I plan to talk about today. Today, I am more interested in the connection of effective dimension with information theory, but I am interested in resource bounds. So it will be more in the line of Eric's lecture on time-bounded or space-bounded Kolmogorov complexity. So I like to use, so the idea is that the robustness of effective dimension is one of its good properties, and let's try to use it also in computational complexity. So, for instance, this is the main result for just effective dimension, that is lower semi-computable Gales or strategies. So for every set A of infinite sequences, the constructive dimension of A, or the effective dimension, as you prefer to call it that way, it can be directly defined in terms of the Kolmogorov complexity. How? Well, just look at the ratio of the Kolmogorov complexity of the n bit prefix of x over n I look at the, oh, I forgot limits. Well, sorry for that. Always typos. Okay. So this is it. This is what's missing in my slide. Okay. So this was should be written. So actually, if you look at the information content in this way, in the way of limits of this ratio, you get constructive dimension. So, well, probably we don't need to define Kolmogorov complexity now. Probably after Eric lecture, even for people a bit outsiders, I think that's okay. So if I want to try to move this characterization to complexity classes, to resource bounds, what can I do? Well, it's pretty clear that space-bounded Kolmogorov complexity behaves pretty nicely in this sense. So if I just define a Kolmogorov complexity with a space-bound F as, well, the minimum program size for a universal Turing machine that of program P outputs W in space bounded by F of the length of W, I just get a very similar characterization. This time I forgot again the limit, I'm sorry. So P space dimension is just the infimum for all possible polynomial space bounds of this quantity, the same quantity. So the worst case of this compression ratio using Kolmogorov complexity is space bounded. But what happens with time? Well, time is always trickier to deal with. Time-bounded Kolmogorov complexity is not an easy to deal concept in this sense. Why? Well, because of invertibility. It's not so clear. So in order to kind of compute the time-bounded Kolmogorov complexity, you kind of need to exponentiate the number of, so the size length. And this is kind of a problem in order to really get a full characterization. Still, a characterization in terms of compressibility is possible, but you need to be careful in choosing which compressors you can use. So if you use a polynomial, a subclass of polynomial time compressors, you can still get a characterization in terms of compression. What kind of compressor? Well, it's a bit of a technical definition, but the idea is that they need to be compressors in which working on two strings, so that one is kind of an extension of the other, you don't throw away all the, so for instance, if you're working on two inputs, W and WU, the computation that you do for input W is somehow useful in order to compute an extension of it. They don't have to be completely online, but the compressor cannot start from scratch. For instance, one example is that if the prefix of the output, there is a long prefix of the output of C of W and C of WU that is common, that's okay. Of course, there can be less trivial examples of this, but this is the idea. The compressor does not start from the beginning. So using this definition, polynomial time dimension can be characterized in terms of compressibility. So at least we have something. So we have a good characterization for effective dimension, okay for P space, Kolmogorov complexity, and somehow a compression characterization for polynomial time. So surprisingly, now I'm going to jump to the more extreme case, that is to the very low resource bounds. And, well, actually, I'm going to start with push-down computations, push-down. You probably kind of understand what I mean. I am talking about a computation by a push-down machine. Meaning well, online access to the input. You read it once from left to right, plus stack memory. Okay? So your memory, you can access it from the top. Okay? So push and pop operations for getting the last symbol. So using these sort of computing restrictions, which are almost the most restricted you can think of, there's even more restrictive ones if you don't have the stack. I mean, you can only deal with finite memory, that's finite state, but this is slightly more than finite state. For push down, you can still get compression is dimension. We can do it for bounded push down, because if you remember your formal language classes, the push-down machines in general are non-deterministic in order to achieve interesting results. We don't want too much determinism. So we control a little bit this non-determinism. We bound this non-determinism. This is where the B comes from. So using bounded push-down, we can still characterize dimension in terms of compression. That's good. It is open for general push-down. So that's an interesting question, whether we can really get a compression characterization using push-down. So, and this is the last case. The last case is finite state. So let me just write a little bit how the world looks like. So effective dimension, it's okay. You can characterize it in terms of Kolmogorov complexity. P space is fine. P, well, if you allow some restriction, restricted P compressors. Then we have push down, in which, yeah, you could define BPD using a compression. And our last level would be a finite state. So surprisingly, finite state devices, they behave pretty well in terms of robust characterizations of dimension, robust characterizations of gambling. This is not news, actually. This has been known for some time, even before we consider effectivization of dimension. So let me just show you like one instance of a gambling strategy using finite state. So this is a two-state automata. What is written in the states is just the ratio that you're going to bet, you're betting. So for instance, in the first state, oh, sorry, okay. Here, you bet, you bet to zero, 2/3 of your capital. And in the second, no, sorry, I'm sorry. The first state is named 0, and the second state is named 1. And your betting in the first state is going to be 2/3 to 0 and 1/3 to 1. And in the second state, 1/3 to 0 and 2/3 to 1. Okay? And this is just the transitions that tell you where to go with the next input symbol. So you just read your input once, and depending on which state you reach per each symbol, you bet accordingly. And as I told you in the last lecture, that we can define finite state dimension using the betting strategies, the Gales that can be computed with this kind of devices. For compressors, traditionally, finite state compressors have been widely used. They are, I mean, in this case, I am thinking about information lossless, meaning that you can recover the input from the output and the final state. So lossless, information lossless means that from the output and the final state, I mean the state you reach when you finish reading the output, you reach, you can recover the input. This is what is information lossless. So using this information lossless, which were the most popular compressors before people started using Lempel-Sieve compression algorithms. So these were well studied. We can define finite state compressions. Well, this is, well, probably you don't need much of an explanation here. Every transition gives you the input slash the output. Okay? And you start with the initial state, which is not marked here but should be 0. And you just concatenate the corresponding outputs. So what we know is that for finite state dimension, you also get a compression characterization using these information lossless finite state compressors. So this is very useful. So it's the infimum for all C that are finite state compressors of the adequate quantity. Limit of C x slash n over n. This, here I am talking about the finite state dimension of a single sequence. But you can imagine that it's the same for a set of sequences. So as I told you, finite state compressors were very popular before Lempel-Sieve. So, but in the mid-70s, Lempel and Sieve presented a series of algorithms, of which we are interested in the one they presented in '78. And for this algorithm, they already proved that our algorithm is better than any of the previous information lossless finite state compressors. And this was, of course, very celebrated by the time. So, for instance, if we define for this particular algorithm LSID just the compression ratio, let's take the limit in order to have the same definition as before, then it was known, since the publication of these papers, that the compression ratio of Lempel-Sieve is at least as good as any finite state device. Okay? So this universality condition was very celebrated at the time, has been used quite a few times for different proofs, and is going to be one of the main ingredients of the algorithm I expect to present maybe today or maybe in my last lecture. Just to, the algorithm has been quite studied. It is known that it can be better than the finite state compressors for certain sequences. So it's a universality, it's pretty close, but there are some differences. Somehow it is considered that these differences happen for a minority of the streets, of the sequences. But it's true because for like a measure one of the infinite sequences, these two quantities, they're very close together. But let's remember that Lempel-Sieve can be slightly better than finite state. So this is kind of our work. We're looking at resource bounds that are even below polynomial time. And we do know certain things about push down. Finite state is, again, very well behaving. But there are still a few open questions if you're looking for an affordable topic to work with, because below linear time, the computational models are pretty detail dependent. So maybe there are a couple of different choices that we should make in the level of, for instance, push down or maybe even linear time. We have looked a bit at online linear time computation, also log space computation, but there are a few choices there in case that deserve to be explored a bit more. So what do we know about comparison between these levels? We do know that push-down compression, here I am dropping the B, but with the B it's also true, it is incomparable with Lempel-Sieve. Okay, well, I didn't say much about Lempel-Sieve because I plan to talk a bit more later, but Lempel-Sieve can be computed in time n log n. It is a pretty formal algorithm with very good properties, but still seems that what you can do with a stack is completely different from what you can do with a Lempel-Sieve. So there are sequences for which push-down compression is better than Lempel-Sieve and the other way around too. Regarding finite state and push-down or bounded push-down, it's clear, of course, that a push-down machine subsumes a finite state, but it wasn't clear if you can really compress more with a stack. And what is known is that there is a finite state random sequence that is not push-down random. Random means you can get infinite success with a martingale. So it's a bit more general than dimension or dimension 1. But even at that level, it is known that finite state random is different from push-down random. Okay? Even with dimension, there is a sequence for which push-down dimension is strictly less than finite state and less than 1. If you were familiar with this topic, there's something missing here. It's not clear what happens with push-down dimension 1. We don't know. Okay? So that's an open question. Is push-down dimension 1 different from finite state dimension 1? As you may have seen written in the last slide, and I will talk about later, finite state dimension is 1 is the same as finite state random. But of course, it's not clear for push-down dimension. Probably push-down dimension 1 is different from push-down random. And it's not clear if these two concepts can be separated. Also, as I mentioned before, we know how to characterize bounded push-down dimension, but we don't know how to characterize in terms of compression push-down dimension. So this is like the first part of what I wanted to talk about today. So compression and dimension, they fit quite well together, but in low resource bounds, you have to work a little bit. So there are characterizations of effective dimension in terms of compressibility of Kolmogorov complexity. They are especially good at the highest level and at the lowest level. That is the lower semi-computability and finite state. And they are good for different reasons, actually. They are good at the unrestricted level because of universality properties of Kolmogorov complexity, for instance, or universality properties of martingales, if you want to see it that way. And they are especially good at the finite state level because the computations are very local, okay? Because they are like an input per symbol computation. So they work well for different reasons. So it's worth studying like intermediate cases and understanding what happens at intermediate levels, because that will give us a lot of information of what is the relationship between things like learning, compression, also randomness. There are like three in the robust levels. These things are equivalent. Where it's not so clear if they are equivalent or not. We want to know exactly what happens in order to understand and to be able to borrow techniques from one thing to the other. So understanding what happens with the lowest level, finite state dimension, or randomness, that is very helpful for number theory, but this I will talk a little bit about next, because of the relationship between finite state dimension and normality, Borel normality. If you've never heard about it, I will talk next. Yes? Sure, please.
First of all, these relations, or some relations between the fractal dimension and Kolmogorov, I know from people like Elvira or Steiger or Finite Omega language. Is this the same, or at least related to what you are telling me with compressors? Or
Omega language.
Then you are to infinity something.
Okay. They have worked a lot about this in these characterizations. Somehow what happens, they were at first interested in this Cantor space.
Yeah.
So they did look a lot at the how far is dimension, house of dimension from compressibility, from cosmograph complexity. The missing piece is that they didn't define effectivization of dimensions, so they kind of have one inequality. I mean, this is for Cantor space, not for omega languages. So I think they want to extend it to other cases like omega languages. But what they did, they look a lot at house of dimension of a set of languages or a set of infinite sequences, and they did this upper bound by the, you know, well, I probably forget the infimum overall. So this was already known by them quite a bit ago, yeah.
Okay, so your point is inequality and the additions with equality.
I'm sorry? My point is that we define this, and this is equal, and this turns out to be an effectivization of house of dimension. In some cases, it is equal. It depends on the A. I will talk a bit more about this maybe tomorrow, but the thing is that for like simple enough A's, like pi2 classes, they coincide. So if A is pi2. And also there is a very recent result by which if you relativize, you get coincidence by taking the best case, the best oracle. There is a recent result which is called the point to set principle, in which if you, so no conditions. So this is the best case of the constructive dimension or effective dimension with oracle B. And actually this is not an infimum, it's a minimum. There is an oracle. So, I mean, that kind of, I think in a very good way closes the circle, because this is cosmograph complexity relative to B. You get back to house of dimension.
I'm aware of these what's called grammar-based compression or straight line problems, whatever, that try to kind of generalize lambda filters. And then again, as it generalizes, I'm not quite sure. This must be something different from your push-down compressor somehow. But on the other hand, grammars, connexity grammars and push-down automata relate.
Let's see. My understanding, grammar compression is kind of the same as push-down compression, grammar-based. I mean, when we wrote this paper on push-down dimension, we kind of insisted very much on the application to grammar-based compressors. But so the idea is that they are not comparable with Lempel-Sieve. That's known, yeah. So they can be better for certain cases, they can be worse for certain cases. Of course, you know, it depends on which world you live in. I mean, the people that really work in practical applications of compression algorithms, they might not be interested in the worst case. I mean, they might be looking at their benchmarks and trying to see what happens with these benchmarks. I'm not very familiar with that, so I mean, I'm not sure how to sell them. I mean, but they were interested in at least remarking like Lempel-Sieve and grammar base is incomparable, but I cannot say more about practical applications. Thanks. No, thank you. That was a good interruption because I tend to kind of lose track. So any other comment on this? So this was the main thing I wanted to explain to you about the relationship of effective dimension and information theory for resource-bounded cases. I wrote all the references at the end. They correspond to the papers in which we prove the different characterizations, separations, etc. I think this last one is related to, even if it, I mean, since it doesn't show in the title, separation of push-down randomness from finite state randomness, I think. All the others, I think, titles are self-explanatory. Okay, so this was like the first part. Now I wanted to move to a different subject, but it is very related to this idea of characterizing effective dimension with compression or with Kolmogorov complexity. It is the effective construction of an absolutely normal sequence. So what am I trying to sell you here? Of course, it's a very recent result. That's one of the reasons I wanted to present it here. But not only because of that. I think it can be an interesting addition to an introduction to effective dimension in resource-bounded settings, because what I'm going to tell you about here is an existence proof. Existence proof in the way, well, I explained you, well, I have a quantitative tool, and what I do is I prove dimension is positive, and from there existence follows. I want to do that. But the thing is, I'm going to do it in a very efficient way. How efficient? Well, around linear time, slightly more than linear time. Time n times polylog. And on the way, I'm going to be exploiting these connections about different kinds of dimension, resource-bounded dimension, mainly a finite state and the relationship with Lempel-Safe. So let's see how, yeah, this is going well. Let me explain. So let's see, as I told you, at the lowest resource-bounded level, finite state dimension meets number theory. I'm going to present soon, in the next one or two slides, the definition of Borel randomness, but you might have seen it before. Sequences with finite state dimension 1 are exactly Borel normal. Finite state dimension is not closed under base change. What does it have to do with everything else? Well, when I look at an infinite sequence, infinite binary sequence, I can easily picture it as represented the non-integer part of a real number in binary. Okay, so this is number x in binary. Or, okay, if this is a binary sequence, it represents this number in binary. And you can change base. You can represent it in a different alphabet using base 3 or base 10. What happens is that with finite state dimension bounds, this matters a lot. So this is related to this idea of Borel about Borel normal. Borel normality depends on the base in which you represent a certain real number. So we will talk next about how to construct an absolutely normal sequence. Absolutely normal means it's normal for every base. So let me jump to what is normal and absolutely normal. So Borel, at the beginning of the 20th century, defined what is called normal. Have you all seen this definition before? Who hasn't seen this definition? You lied. No. Sorry. I say that to my students. I'm sorry. This was just. I didn't mean it in this audience. I know you don't like. So just for explanation, so given a real number alpha, this number is normal in a certain base. If you look at the infinite representation of number alpha in base B, and you just kind of see whether there is a pattern that appears too often. What does it mean? Well, you take a single W, a finite sequence. Well, let's see if you're in base B, sequence of digits in base B, a finite sequence, and you count how often it appears. So you count how often it appears in the first n bits of the base B representation. And well, if this was kind of random, how often should it appear? Well, it should appear around 1 over b to the w. That would be like the fair share of number of times that you should have it. If you take the number of, so this would be n alpha wn is the number of times that w appears in the first n base b symbols of alpha, and then over n. So normal means that no pattern is appears too often or too little. So everything is kind of balanced. So zeros and ones are balanced in binary, 0, 0, 0, 1, 1, 0, 1, 1 are balanced in binary, etc. And in other bases, similarly. So as I tell you in words here, the asymptotic empirical frequency of W in base B, expansion of alpha is B to the minus the length of W. Okay? So alpha is absolutely normal if it is normal in every base. Okay? So these were both defined by Borel. So you can guess that he was thinking they are not equivalent concepts. He was already guessing separation for different bases going to be achieved. And in fact, in the 60s, Castles and independently Smith, they already constructed a number that is normal in base 2, but not in base 3. It's a pretty construction in case you're curious about this topic, but I'll move on. So here are a couple of examples of normal sequences. I don't think I would call them natural, and they are normal in one base. I would bet none of them is absolutely normal. So the first one is Samper Knowns sequence, which is just 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, just write the numbers with all the digits. So this could be in base 10. I mean, this could be the Chaperone sequence in base 10. You can write it in other bases. You would get probably different numbers. And they are normal in the corresponding base. No clue that they are normal in any other base. And Copeland-Erdős sequence has the prime numbers. Okay, prime numbers one after the other. 2, 3, 5, 7, 11, 13, etc. Okay. So, as I tell here, they're pretty far from natural. And on the other hand, Borel already proved that almost every real number is absolutely normal. Okay, so there's a big gap. Okay, really not known, natural, absolutely normal real numbers, but almost all of them should be. So, well, you may be familiar with this kind of ideas about pi, e, square root of 2, even the Neperian logarithm of 2. People think they are all absolutely normal. There's no clue why. Well, or maybe there are clues, but they don't go all the way to proving that they are absolutely normal. So actually, it's mostly computational. I would say computational simulations are the main proof. I don't know if anybody here can tell me wrong. I think they are believed to be normal because all the computational simulations, they keep adding digits, and they don't seem to have a pattern, so they're probably normal, absolutely normal. I mean, no matter, this is not, doesn't seem to depend on the base you choose, so these numbers could be absolutely normal. So no such natural example of a real number has proven to be normal in any base, actually. So these numbers, it doesn't matter which base you choose, it is known now, not known that they are normal. The conjecture is that every algebraic irrational is absolutely normal. Not only this nice example, or these famous examples, but every algebraic rational. But of course, this is just a well-known open problem. Nothing else. In cryptography, they use these numbers a lot. These numbers means this. And they think they use them because they believe they are absolutely normal. And they call them nothing up my sleeve numbers. Kind of numbers that don't hide any pattern. But this is practical cryptography. So we are interested in how efficiently we can construct an absolutely normal number. Actually, Sierpinski and Lebesgue already gave constructions of absolutely normal numbers, but they were not effective at all. I mean, they were not constructive, actually. They were based on limiting processes that, of course, they had to converge for certain reasons, but not clear how to effectivize them. Whereas Turing, in 1936, apparently, because this is an unpublished manuscript, you probably kind of know this story, is written on the back of the paper where he introduces his computability main notions, etc., but it's unpublished. He gives a constructive proof that almost all real numbers are absolutely normal. So he kind of proves effective measure is 1. Kind of gives implicitly this could give a construction. Let me tell a bit more about this. So, okay, and then he derived constructions, actually, of absolutely normal numbers. Actually, he doesn't only present the effective measure proof. He also gives the construction of the absolutely normal numbers. And I want, I like to at least credit Turing a bit more, because I think his contribution was far more than was known at the time, actually. Because we did believe that Schmidt was the first one to construct absolutely normal numbers until very recently. And the most surprising part is that this Turing's idea of effectively measuring absolute normal numbers came before, before things like Martin Löw, von Mises, Solonomov, Kolmogorov, all these people that formalize what is effective measure, what is randomness. I think this is kind of a very important unpublished paper. Figueira, Becher, and Pichi did a very good work 10 years ago of republishing this paper and publishing it and explaining exactly how far the proof did go. So from all this, I want to stress the importance of this first result. Now it's different. Now we already know that normality is a type of randomness. We have a big advantage. So very recently, people have started writing algorithms, effective algorithms for absolutely normal. How effective? Well, Becher, Heiber, and Slaman, and other people also kind of at the same time, but they were the first one to publish a clean and good algorithm. They compute an absolutely normal number in polynomial time. What does it mean? It means, so you want to compute a real number, alpha, and then the sequences corresponding to each base representation, they need to be normal. Okay, so what they do compute is the base B, the base 2. Representation of this real number, but this base 2 representation corresponds to absolutely normal, okay? So if you change it to another base, it's still normal. And what does it mean polynomial? Well, it's polynomial in the number of binary digits. Of course, it could be polynomial if you could do the construction in a different base, it could still be polynomial. So it's time n squared polylog n. Okay? So my plan, which is maybe a bit ambitious for today, since I have the opportunity of coming back tomorrow, I think I'm going to keep our algorithm for tomorrow, if that's okay. I was thinking about talking about something else too, but well, I like this algorithm. I like to talk a bit more tomorrow about this algorithm that is slightly better than theirs, because we can drop this n squared to n. So our algorithm is n polylog, and we kind of justify it's almost the best possible because this n polylog is very close to linear, and I mean it's not computation model dependent. Linear time is nothing. What is linear time? Turing machine, RAM. They correspond to different notions, but n polylog is the same in every natural model we can think of. So let me stop here and take some questions. And tomorrow, if you come back, I'll start talking a bit about how we get this nearly linear time algorithm for absolute normality. And as I promised, it will be based on an effective existence proof based on dimension randomness. Thank you. Yeah.
Can you and Hitchcock have something between when you diagonalize against all linear time materials? So if you diagonalize against all linear time materials, you will get an absolutely normal number, right?
That was polynomial time, unfortunately.
Oh, okay. Is that greater than x?
It was, yeah, we did some, yeah, I'll talk about it tomorrow if I have the time. But yeah, there's base, so the idea of whether dimension is base independent, like if you change base, you still get the same dimension. We deal with polynomial time dimension. And I think we needed like an n to the cube or more factor. We did it very clumsily, probably.
It's just a personal opinion, but I think that's the cleanest of all these results. Conceptually.
Actually, we use part of that construction. I mean, the idea of how to change base from, you have a martingale for binary sequence, and you want an equivalent martingale, but in base B, that's kind of, yeah, we learn it there in that paper, yeah, thanks. Yes?
So the running time to get there, if you view the binary sequence as the characteristic sequence of a language, then you get a language in exponential time.
Yeah.
So is there any hope that you can get something much better than that, where on input I, you get the ith bit in a reasonable amount of time?
I guess, but as I tend to believe we would be cheating a little bit in the model, but I guess the poly logarithm, we could try to get like a smaller growing function. Yeah, so yeah, we get a language that is between 2 to the n and 2 to the n square. So yeah, we could get something closer to 2 to the n, yeah.
But I mean, could you get something, closer to p, like polylogarithmic time, the length of I?
I don't know how to do it because, yeah, I try to deal with, so normality means I could just, I don't know, I'll think about it. But my impression is that naively, if I really want to look at the patterns everywhere, I need to at least read the string once. If I leave pieces of the string, of the sequence without reading, I don't know. How can you be sure that it's normal? Yeah, I don't know.
If you fix a particular place, so Martin's house has a known paper where you construct a normal, base 2 normal in AC0. And it's a very cheap trick where basically it's a pattern that repeats for a long time. Right. And there are transition periods. And the transition periods are given as non-uniform and vice versa. So
okay.
Look at the time.
I mean, that was predates this.
Yeah, that's
I see. Okay. So yeah. That's an interesting question. The thing is that maybe for a single base, you can play these tricks. But this idea of getting absolutely normal, you kind of need to control like martingale growth all the time. If you.
So Jack said that if you try to change that number in base 2, then it wasn't normal in base 3.
Yeah.
Right.
Yeah. Still.
They're easy to generate.
Yeah, sorry, you're right. When I mentioned chap, I didn't say that result. Yeah, that's true. I mean, still, I couldn't rule out completely the possibility, but I tend to think that I really need to control the whole prefix of the sequence for this. But let's.
So does this have any, would there be any complexity consequences? I mean, we're talking about finite state randomness of languages in P. Is there a reason?
Of course, finite state randomness is base dependent. I cannot expect to get very far with. So, I guess, yeah, you would have to deal with these close to linear bounds and try maybe to play with things like push down, etc., trying to see if you could do something like this in order to get like cheaper sources, randomness sources. Yeah, that's an interesting question, and I think that investigating these notions that are very close to linear randomness or linear dimension would be very interesting, but I really don't know.
Because with Samir Dada, we did some work on, let's see if I can even remember what the results were. I think for any algebraic number, if you view that number in binary as a language, I think it lies in the counting hierarchy.
Mm-hmm.
You know, there's no reason to think that that's optimal for the basic counting. Yes, it's a lot less than exponential time.
Yeah, yes. Yeah. Yeah, I guess I wasn't thinking that far below. I mean, we did look a little bit at log space, but we didn't go that far as polylog time and things like that. Yeah, but that's a good idea.
One thing which has been interesting in all of this stuff has been that the Betcher and Slayman and Knowles, they've been using these techniques to get new results in number theory.
Yeah, no, I plan to talk a
new
bit.
results in number theory, the number theorist care about, not new results in number theory, the logicians care about. You know, so it's a nice example that methods from computability and complexity theory can actually give insight into things that other people care about.
Yeah, I was kind of leaving this for the end of the construction, but yeah. It's the thing is that the construction by I mean, it's not only a competition of time bounds. Actually, they do get very good properties in the absolutely normal sequence that they construct. That, for instance, yeah. So the important ingredient, I think, in order to get these constructions is that their discrepancy is kind of low. They've recently proven as low as you want, meaning that you get very quickly. I mean this limit, that defines normality. It converges very quickly, and that helps them a lot to achieve other properties of the number they construct. Yeah.
It's kind of the same deal of the people who are using Commodore complexity to get things in equator theory, which is kind of
Yeah. So I don't know exactly what I will be able to cover tomorrow. I mean, my plan was kind of go back to geometry and tell you a little bit of this kind of new results, but I don't know if I'll have time for everything. So I'll try to choose what to do with my 50 minutes tomorrow. Uh-huh.
Is that hard?
Okay, that
if MP has P measure bigger than 0, then SAT's exponentially dense.
Oh, okay. We can. No, I can give you the outline.
It's not hard.
I mean, okay, let's see. I think it's reasonably easy to explain, but I'm not intending that. Okay, I'll promise I'll spend a few minutes with that tomorrow. Okay, thank you very much.